Now let's turn our attention to example number 2. I want to find the flux of F across sigma, where F is given by this vector field, and sigma is the surface that's bounded by the cylinder and these two planes. That's the plane x equals -1, which would be over here at the back, and x equals 2, which is over here at the front. So I get this kind of can-like shape, and that's what I want to work with. Now, I have a couple different ways I can attempt to do this. And I can see here that one of these ways is going to be significantly easier. If I was to go ahead and actually think about this in terms of section 5.6, I would recognize that my surface sigma is actually composed of several different surfaces. I have this cylindrical part, which I could call sigma 1. I have this kind of back circular part over here, which I would have to call sigma 2, and this front circular part would be sigma number 3. Now, if I wanted to find the flux across that, that's totally fine, but notice I'd have to find the flux across sigma 1, then sigma 2, and then sigma 3. Note that this is just like what we saw with the cylinder that we had back in section 5.5 when we introduced the idea of a surface integral. That if I have multiple surfaces that build kind of one big solid, or big surface, I can just tackle surface integrals by doing each piece one at a time. And since flux was just a special kind of surface integral, we apply the same idea. But of course I can see that's going to take a lot of work. I'd have to understand which way I want to orient all these different surfaces, understand how I orient it, compute 3 different types of integrals, one for each one of these surfaces, and that can be a lot of work. However, I will notice here that sigma itself, when I take a look at it, is definitely a closed surface. So because of that, I can instead trigger in my mind the idea that the divergence theorem may be helpful. Instead of dealing with all 3 surfaces on the boundary, how about I just do a triple integral with the solid that's enclosed? Okay, so let's see how we would start to do this. Let's assume that sigma here is going to have a positive orientation. So how about we say, let sigma have a positive orientation. Remember, for a closed surface, that means that my orientation is, I have vectors that are pointing out from this. Okay, so if I assume that this is going to have a positive orientation, again, I know that we're going to try to calculate the flux integral over sigma, so that's f dot n ds. That's what I would like to compute. Of course, then, we can say that we see that sigma is the boundary of the solid G, which we can say is given by a bunch of x, y, z points, and I know how to define them. Very clearly, I need to have y squared plus z squared be less than or equal to 1. Notice if it's equal, I'm going to get a point that's on the cylinder, and if it's less than, I'm going to get something towards the inside. But I also have restrictions on the value of x. That is, x specifically has to go between -1 and +2. So this is my surface, or my solid of G. And so, by the divergence theorem, we can say that my double integral, my f dot n ds over sigma, is equal to a triple integral over G of my divergence of F dv. Now in the previous example, we had this divergence come out to be 1, and that just meant we had to find the volume of the solid. We can see if that comes out the same here, but I would very likely doubt it based on the complexity of our vector field. So let's see what we come up with here. The divergence of F means I'm going to start by doing partial with respect to x. It's going to be a 3y squared plus partial with respect to y. It's going to be 0. And then partial with respect to z is going to be a 3z squared. So I definitely don't get a 1 in here, and that means I can't just simply do the volume of my solid. I'm going to actually have to set up this triple integral based on ideas that we talked about back in chapter 4. So let's go ahead and think about what we're working with here to think about how I could actually set up bounds on this region and also set up my differentials. So if I'm working with a cylinder here, it might seem like it could make sense to try to tackle this using cylindrical coordinates. So maybe I can go ahead and see this. I'll say that we see that if x is going to be wedged between -1 and 2, that can act as kind of like a floor to a ceiling if I imagine rotating this solid a bit. Then the rest of this is just moving in a circle. And so I can say and the projection of G to the YZ plane is, well, it should just be the unit circle, right? Because I had already here a circle with radius 1, and so then I know how we could actually go ahead and represent that. So I think I can go ahead and state that my triple integral over G of 3y squared plus 3z squared could instead just be re-expressed as my triple integral, where I'm going to have, let's see, 3y squared plus 3z squared could be rewritten as 3r squared, and then I'll do r dx dr d theta. My x values again went from -1 to 2, and if I'm dealing with a unit circle, my r is going to go from 0 to 1, and my theta is going to go from 0 to 2 pi. In fact, this is a super simple integral to calculate. I'll leave it for you to double check the details, but I ended up with a final answer of 9 pi over 2. The important thing to note here is that when I use the divergence theorem, it's a different way again to calculate the flux. I could have again calculated the flux by grabbing the flux across all three sides. That's a lot of work. However, since I have a closed surface, I can go ahead and use the divergence theorem to shortcut the work. The only thing that I have to make sure I understand is the ideas we talked about in Chapter 4, which allows us to set up this triple integral so it can be calculated.